Hello, I am Rahul Gopinath, a postdoctoral researcher at CISPA Helmholtz Center for Information Security. Today, I am going to talk to you about how to tame grammar fuzzers to generate you precisely what you need. To set the stage, let us take a look at what fuzzers do. During fuzzing, we feed random inputs to a given program and check the program behavior. If it crashes, then we know that we have hit a likely bug. Here is another input that is accepted by the program. And here is another that crashes the program. From these cases, we can produce a hypothesis that this crash was caused by an empty key in an object. Unfortunately, this kind of debugging is not always easy. For example, the input that produced the crash may be huge. So it is often useful to identify a smaller input that causes the crash. Fortunately, there is a way you can do that called hierarchical delta debugging. The idea of hierarchical delta debugging is that given a context-free grammar of the input, we can iteratively reduce the given input into a much smaller input, such that the new input still reproduces the behavior. The next question is, what actually caused the failure? This was tackled in our ISTA paper on DD-set. With DD-set, the idea is again simple. We start with a parse tree of the input. Then we look for parts of the parse tree that can be replaced with random values of the same kind. For example, the node JSON cannot be replaced with random values. Same with ELT and same with object. With items, we try to replace a smaller portion of the input, but that doesn't work consistently either. We recurse our item and our string, which shows that that part of the input is not abstractable. However, coming to ELT, we see that we can replace ELT with pretty much any other ELT and still reproduce our behavior consistently. That is, ELT can be abstracted, and we find our abstract representation of the input, a simple object with an empty key and any element as its value. This was published at ISTA. However, this leaves one question unanswered. How can we generate more failure-inducing inputs using this abstraction? We can of course generate numerous inputs with random values substituting our ELT non-terminal. However, these inputs do not capture the complete behavior. In particular, consider the following inputs. These inputs also cause the same behavior. However, they can't be generated from our abstract input. That is, the abstract pattern we mined can occur in other contexts. So what we need is contextualization of our mined pattern fragment. And this is the first step in input algebras. First, as before, we start with the abstract parse tree generated by DD-set. Then we look for and extract the fragment of this parse tree that captures the essence of the bug. And this can be done automatically by simply trying to capture all concrete parts of the input. And it can also be further refined manually. And in our example, an input is failure-inducing if it contains a non-terminal item with an empty key. We thus extract the subtree that contains this pattern. This is the evocative subtree. Once we have the evocative subtree, we can simply collapse it for the evocative fragment. The root node of the tree becomes the name of the evocative fragment. Here, we name our evocative fragment item E. The body of tree is collapsed, with abstract patterns left as it is. This becomes the definition of the evocative fragment. In our example, the body is the empty string colon non-terminal ELT. The next step is to linearize this evocative subtree into a linear grammar that will precisely reproduce this tree. And we accomplish this by tagging the non-terminals in the tree nodes with monotonic suffixes such as E0, E1, E2, etc. Then we look at where we can insert our evocative subtree. For this, we start with the root node of our tree. Here, our root node is an item. So we mark terms in each rule of our grammar that can generate the non-terminal item at some point. We remove any expansion rule that can't generate an item and remove any resulting empty definitions. Then we take each rule and duplicate the rule sufficient number of times such that only one non-terminal is marked. For example, the second rule in the item get duplicated to accommodate marks in non-terminals item and items. Similarly, the second rule in ELTS gets duplicated to accommodate marks in ELT and ELTS. We now mark the corresponding keys in the grammar and we have the reachable grammar. Then we combine the reachable grammar and the pattern grammar we produced earlier. Along with the definitions in the original grammar, this gives us the final focus grammar corresponding to our evocative pattern. Using this evocative grammar, we can now produce an infinite number of inputs, all guaranteed to reproduce the behavior. In particular, our grammar now has two interesting properties. The first is that any input generated from this grammar will contain at least one fragment that induces the given behavior. If it is used as a validator, then it can recognize any and all inputs that contains a fragment that can induce the given behavior. Now, the next question here is, what if there are more patterns? That is, say we have another crash that happens when the JSON string contains a key with a value of null. One may want to generate inputs such that both conditions are satisfied. That is, the JSON fragment contains both an empty key and a key value of null. On the other hand, we may need input such that it triggers the empty key, but null values are guaranteed to be absent. Finally, one may also want to avoid triggering the crash by guaranteeing that neither patterns are present in the input. All these constructions can be produced using input algebras. The logical operations between different patterns are produced by beginning at the starting symbol such as JSON and then continuing from the recursively by evaluating each term in the expansion rules. This produces the complete grammar that is equivalent to the evocative expression specified. Note that the specialized evocative grammar is a simple context-free grammar. That is, this grammar can now be fed into any grammar fuzzer producing expressions which are guaranteed to contain at least one empty key and no null key value. In fact, we can combine any number of patterns producing arbitrary logical predicates. That is, using our constraint language, we can embed almost arbitrary constraints into a base grammar, producing inputs that obey such constraints and corresponding predicates. Now, what kinds of constraints are possible? It may be to cover various parts of the code, or not to cover various parts of the code, or any combinations thereof, or to ensure that the variables and types used are compatible, or to ensure that a common bug is not triggered in generating inputs. All these required custom generators previously, which limited their effectiveness. With our technique, such properties can be mined directly from the program and used in combination with other properties. Finally, consider these issues from real-world projects. Each of these real-world bugs are from different JavaScript interpreters. How do we verify that the root cause of these bugs are fixed? What we can now do is to first abstract them into their abstract patterns, and each of these abstract patterns will now form the seed for focused fuzzing, making sure that the bug is actually fixed. However, that is not enough. Often, new bugs hide between feature interactions. So we want to make sure that our fixes are effective even in the presence of other bugs. And we can now test our bug fixes easily against arbitrary combinations of behaviors. For example, we can verify that the inputs containing both closure bugs does not crash. And we can also verify that inputs containing both Rhino bugs does not crash. Or that picking one of Rhino and one of closure bugs behaves as expected. Or that none of these bugs are triggered. That is, using our technique, we can completely train grammar fuzzers into producing exactly what we need. Beyond testing, that is precise control during fuzzing and for validating fixes, our input algebras have a number of other uses. They can be used as a mechanism for validating inputs, removing dangerous inputs before it reaches the parser. And they can also be used as an alternative to regular expressions, forming supercharged recognizers. And such recognizers can be used for static analysis of code bases, looking for specific bug patterns. And we can use input algebras for generating data structures for API calls. All these form our future work. Thank you for listening, and I'll be happy